Welcome back, everyone. So before the break, we talked about how to use the Stirling numbers. Essentially, the Stirling number table that you're looking at here is describing the number of ways to distribute m different objects into n identical containers such that none is empty. Okay, so this is actually a nice problem because there's a nice equation that goes with it. That is that we have this s of m plus 1n equals Sm n minus 1 times plus n times S of Mn. So this is an equation. We're not going to prove it, but this will help us to determine what the next row of the Stirling numbers is. And before the break, we mentioned that this is actually very similar to the Pythagoras theorem, or sorry, not Pythagoras theorem, the Pascal's theorem, where we had the Pascal's triangle. So the other thing that we should mention before we move on here is that the number of onto functions, which is the number of ways to distribute m different objects into n different containers such that none is empty, which is the onto function, can be found by simply multiplying n factorial to whatever s of mn is. So remember that long equation we wrote out earlier? We no longer need to remember that, although it's probably a good idea to know what the parts are. We don't necessarily need to write out the whole summation whenever we want to find an onto function because we have this table for s of mn. All right, so a couple of things about S of Mn, about how to apply this equation. There is this this row, for example. If I ever wanted to find, let's say, S of 7, 3. Okay, so if I wanted to find S of 7, 3, if I don't know how to generate this row, and by the way, I want you to see how this table is made up. Uh, all the ones here along this column and all the ones here along these diagonals are our base cases. Okay, so much like in the triangle, the Pascal's triangle that we saw before, there are base cases, right? The sides of the triangle. Here we have base cases as well. So if we take a look at this column, it's indicating all of the cases where n is equal to 1. So the idea is if I only have one box, how many ways are there to put m objects, different objects, into that one box? And the answer is only one, right? There's only one way. You put all the objects into that one box. Similarly, if the number of objects is equal to the number of boxes, how many ways are there to put the objects into the boxes such that none is empty? Well, again, the answer is that we have one way because you just put one object into each of these boxes. Now, I want to be clear here that these boxes are identical. These are identical boxes, so it doesn't matter which box you put it into. Right. So I hope everyone is happy with the diagonal as well as this first column here, but the rest of these can be generated using this formula. So again, if I wanted to find out what is S of 7, 3, but I knew what the previous row was. Okay, so I can find S of 7, 3 by taking S of 6, 2 plus, in this case, it would be n times, so 3 times S of 6, 2. Sorry, 6, 6, 3. All right, so S of 6, 2 and S of 6, 3 is going to make up this number. So S of 6, 2 is 31, and then we do 3 times 90, which is going to give me 301. Okay, so just verify that that is correct and verify that that is an application to this theorem. Okay, so just understand that this theorem is true. For a full proof of this theorem, please consult a textbook, but I'm not going to go through the proof here, only to say that this theorem is very important because it's a recursive definition and allows us to be able to find all of the upcoming rows in our table. Okay, so let's go through a couple of questions that allow us to be able to kind of um, use this table. So what kind of questions can we take out of this table? Now, the obvious one would be finding the onto functions, right? So the number of onto functions from A to B, where the size of A is, let's say, I don't know, 6, and the size of B is equal to 3, right? So we did an example earlier like this where I was feeding the kids the sandwiches or something like that, right? So I have 6 different sandwiches and I'm giving it to the 3 kids. And so in this example, we are looking for the number of onto functions from 6 items to 3 items. So we are looking for S of 6, 3, but we're doing the 3 factorial before that. Right, so much like what we had in the previous example, the number of onto functions from 5 to 3. Here we have the number of onto functions from 6 to 3. And so 6, 3 is 90. And 3 factorial is equal to 6. So if you remember earlier, we had the number 540, and that's where it came from. All right, let's do another quick example here. If I said how many ways to distribute 6 different objects into 3 identical boxes. Okay, so let's take 2 scenarios here. One where the boxes are empty. So sorry, no box can be empty. No box empty. Okay, so I just want you to see that this is a direct application of S of 6, 3, right? So number of ways to distribute 6 different objects into 3 identical containers is S of 6, 3. So we can just read off this diagram and the answer is 90. Now, on the other hand, for B, if we say the boxes now can be empty, so boxes empty allowed. Okay, now if we do allow empty boxes, it's very similar to saying that I'm going to distribute 6 objects into 3 boxes with none empty, or 6 objects into 2 boxes with none empty, or 6 objects into 1 box with none empty. So the short answer here is that if I want to say that empty boxes are allowed, then I'm going to take the summation along the row up to the point that I need it. Okay, so here the answer is S of 6, 1 plus S of 6, 2 plus S of 6, 3. Okay, so again, if you allow empty boxes, you could allow 1 empty box or you can allow 2 empty boxes. All right, so that is basically the answer. All right, so anyways, just a very quick example to show you how we would be able to use this chart for answering specific types of counting problems. All right, nextly, next, let's take a look at different types of functions. So there are special functions called a floor function and also a ceiling function. So there's specific applications for each, but I just want to introduce it here. I just want to give you the definition here and perhaps give a few examples. And in the next subsection, we're going to talk about an application of the floor and ceiling function. So let's start with the floor function. All right, so the floor function, the definition is that we have a function f that maps real numbers to integers. Okay, so real numbers to integers. Now remember what R means. R means any number that you can think of, and Z means integers. So I'm mapping real numbers to integers, and in the floor function, it assigns the x that is a real number to the largest. Now, I'm going to underline this because it's important. It maps to the largest integer that is less than or equal to x, and it's denoted by something like this. So it's kind of like a square bracket, except it's a lower square bracket. Okay, so if you're typing this in, I would just type something like floor x. Right, so I think that would be the best way to type it into a computer or anything like that. That's probably the best way to represent it. Okay, so for floor x, you are basically rounding down on a number line. Okay, so for example, if I had the floor of 3.5, this is equal to 3, because if we look on a number line, it would be 3, it would be 4 and 5, and 3.5 is around there. It should be in the middle. So 3.5 is around there, and the largest integer that's less than or equal to x is going to be 3. Right, so we're rounding down, and we want the largest integer that is less than or equal to x. Okay, similarly, if I take something like negative 3.5, so this is negative 3, and then we have negative 4, negative 3.5 is around there, right? So the floor of negative 3.5 is going to be minus 4. So we're rounding down, once again, the largest integer that's less than or equal to 4. Now, if we're dealing with a integer, then the floor is simply that integer, because it does say in our definition that it's the largest integer that is less than or equal to x. So if x happens to be an integer itself, then the floor is just that integer. Okay, that's the definition of the floor function. And the floor function is used again to round down. Okay, so there are certain applications for that. We're going to talk about that in a second. There are some applications for also what we call a ceiling function. A ceiling function is what we're going to apply in our next subsection, but the ceiling function looks exactly the opposite of the floor function. In fact, it is kind of like the dual definition of the floor function. So for the ceiling, it is a function that maps real numbers to integers, same thing as before, and it is the function that assigns an x that's in a real number to, this time, the smallest integer that is bigger than or equal to x. Okay, and it's denoted something like this. So again, just like the square bracket, except it doesn't have the bottom, right? So it's kind of like the top. And in this case, we are rounding up to the next integer. So again, if you take a look at the number line that we had before, the ceiling of 3.5, the ceiling of negative 3.5, and the ceiling of 3. So if we take a look at that number line again, the ceiling of 3.5 is going to be 4. The ceiling of 3.5, negative 3.5, is going to be negative 3. And for the integer, for the whole number, it's still the same. So this is 4, this is negative 3, and this is equal to 3. All right, so it turns out that there's a lot of nice properties that come from floor and ceiling functions. I'm not going to talk too much about them right now. You can, again, refer to the textbook if you're wondering what these properties are. But anytime you see two numbers in which their floor is equal to their ceiling, then that means it must be an integer. In fact, if you ever need to prove that something is a whole number or something is an integer, maybe one of the ways to do that is to use the definition of floor and ceiling and show that they must be the same. Okay, so that is one strategy that we can use for showing that. Okay, so I mentioned that there is an application for floor and ceiling functions, specifically for ceiling functions, but that is called the pigeonhole principle. So what I want to start with right now is just to give the definition of pigeonhole principle and what it's used for, and this is the most basic pigeonhole principle. It says if k plus one or more objects, now I'm going to circle the word objects, are placed into K boxes. Okay, now I circle these two words because every pigeonhole principle problem is going to rely on these two things, objects and boxes. Okay, so the idea is this. When we sell pigeons, we have a bunch of boxes to put these pigeons in. And we don't want two pigeons to be in the same box because then they don't have enough room to move, right? So the idea is that if you have K plus one or more pigeons and they're put into K boxes, then there's a guarantee that there's at least one box, there's got to be a box with more than one objects inside. Now, you might look at this and say, well, obviously, right? It's intuitive that what this is saying. But it turns out that in a lot of proofs, the pigeonhole principle is actually very important to that proof. So let me just write a statement, first of all, that among a group of 13 people, there's at least 2 people born on the same month. Okay, now again, this might be a very intuitive statement, but we're going to show this using the pigeonhole principle proof. So the idea is that we need to assign what the objects are and what the boxes are. Okay, so in this case, our boxes is 12 because the boxes correspond to the months. There are 12 months and there are 12 boxes. And each one of these people have to go into one and only one of these boxes. And again, this is a requirement. Whenever you have a pigeon, it must be placed into one and only one of these boxes. Okay, so here we can say that we have k plus 1, or sorry, we have the number of people is equal to 13, right? So therefore, we can use the pigeonhole principle statement to say that there are 13 people and there are 12 months, and therefore there's a month, there's a box with 2 people inside, 2 objects inside. Okay, so that is the idea of the pigeonhole principle, and I'm going to rewrite this statement many times. But again, let's try to get the gist of the pigeonhole principle. We're basically making an argument that one of these boxes, it doesn't matter which, I don't know which one it is, but there must be a box that has 2 objects inside, right? That has multiple objects inside, and a lot of times that is really the use of a proof like this. Okay. Now, let's move on to something a little bit more general. The generalized pigeonhole principle goes like this. If there are n objects, now this time we're not saying k plus 1, right? But there are n objects and they're placed into k boxes, then there's a guarantee that there's at least one box containing n over k to the ceiling objects. Okay, now this is just a equation that we have to remember, right? There's a guarantee that one of these boxes is going to have this many objects inside. Okay, now in a second, I'll show you where this equation is coming from, but let's do this example first. All right, among a group of 37 people, how many are guaranteed to be born on the same month? Okay, so this is actually very similar to what we were talking about in the previous statement, with the exception that we can now guarantee multiple, not just 2 people in the same month, we can guarantee multiple people in the same month. All right, so the first thing we need to do for pigeonhole principle is we need to identify our n and identify our k. N here is equal to 37 because we have 37 people. Okay. K is the number of boxes that we have. In this case, it's the same idea. We still have the number of months, which is 12. Okay. So now we can rewrite our pigeonhole principle to say this. There exists a box. Okay. Now, in this case, the box is the month, right? So there exists a month that contains this many. Now, I should add the word at least, but if I don't add this in the future, you know what I'm saying, okay? So there's a box, there's a month that contains at least this many people, which is objects. Okay, so so our n over k here is 37 over 12, which is equal to 4. Okay, now let's consider what this equation is telling me. If, let's say there's 36 people, okay, if I have 36 people, and let's say we're really fortunate in that we can distribute all 36 people into distinct birthdays so that there's 3 people in each month. And that could happen, right? So if I have exactly 3 people in each of the months, then I have 36 people. Now, where does the 37th person go? Well, the 37th person has to go into one of those months. So that's a guarantee that there has to be one month that there's four people. Now, this is a kind of a pessimistic definition because if you think in reality, if I have 37 people, chances are I'm going to have more people born on the same month, right? It's probably like September or something like that. I notice a lot of people are born in September. But the pessimistic guarantee is that we can have a month that have four people, at least four people, and that's the guarantee. And a lot of times when we do a proof, the pessimistic guarantee is good enough. Okay, so I'll leave it at that. But I'm going to apply this equation again and again. But I hope you see that where the ceiling is coming from. 37 divided by 12 is 3 point something. That means it's above 3, right? It's above 3. So when I want to guarantee how many people are in a particular box, I can take the ceiling and it goes up to the next integer. Okay, so again, I hope you can see where this equation is coming from. All right, let's do a slightly harder problem. A bank has 360,000 customers and uses PINs of 4 or 5 digits. How many customers are guaranteed to have the same PIN number? Okay, now here's a little trick. Whenever you see the word same or the word identical or something along those lines that means same, the next word is typically telling you what the what the boxes are. In this case, it's the pin number. Okay, so the pin number is representing the boxes. In our previous example, the word same, the word that comes after that is month. So we know the month represents the boxes or the K. So right away, because the word same pin, I'm going to say that the K is represented by the pin numbers, and the pins are made up of 4 or 5 digits. So how many pins are there altogether? Well, 4 or 5 digits, they could be 0 through 9. So that means for 4 digits, I can have 10 to the 4 different pins. Now, please check my math there, but essentially I have 4 boxes to fill. Each box can be filled with uh, each of the 10 digits. It's with repetition because theoretically I can have a pin like 0000. It's not a good pin, but we could have that. Or we could have a pin like 5 digits. And so we get the number 110000. Right? This is how many boxes, how many pins that we have. Now, on the other hand, what is the n? Well, we're told that there are 360 customers. And this is going to be my n, going to be the number of objects that I have. Now we have to be very careful. We don't want to say that any other number that we get, we're just going to throw it into the objects, but we have to make sure that in this case, that every customer has a unique PIN. Is that true about this statement? Yes, it is. So that's why every one of these objects goes into one and only one of the boxes. That is a requirement here. So we have to make sure that that's what we're thinking. Okay, so again, we can rewrite that there exists a box with at least, I'm not going to write that, but at least this many objects inside. All right, so the box is our pin. So there's a pin with at least this many customers inside. So what is n over k here? Well, it's 360,000 over 110,000. I think this answer is equal to 4 again. So the guarantee is that there's at least 4 customers with the same pin. Now, in reality, again, it's probably a lot higher than that, right? So it's probably a pin that is very easily guessed or something like that. But I hope you get the idea. Okay, so earlier, I said that pigeonhole principles can be used in order to make certain proofs of statements. So let's do a couple of pigeonhole principle proofs just to show you how those are used in practice. So The first proof goes like this. Let A be equal to 1, 2, 3, 4, 5, all the way up to 10. Show that any subset of size 6 has a pair that sums to 11. Now, I said earlier that you should look for the word same in our statement. Now, here I don't see the word same, so we have to guess at what the box is. What similar characteristics do we have about these objects? And it seems here that what we're looking for is a pair that sums to 11, right? So all of these objects have a characteristic that it sums to 11. Okay, so I'm going to say for my K that the boxes is going to be those, okay, that sum to 11, pairs that sum to 11. Okay, now how many pairs do we have that sum to 11? Well, you can think that we have 110, right? So 110 is one of them. We have 2, 9, we have 3, 8, we have 4, 7, we also have 6 and 5. So we have 5 boxes altogether. So the size of K here is equal to 5. Right, so we have 5 boxes. Now, if you imagine that I have these boxes corresponding to 110, another box corresponding to 2, 9, 3, 8, 4, 7, and then 5, 6, I can look through any subset of size 6. So let's just generate a subset of size 6. Let's say we have number 1, 2, 4, 5, 7, and 9. Okay. Now, what we're saying here is that there is a guarantee that there's going to be two numbers, at least two numbers, at least a pair of numbers that are going to sum to 11. Now, in this case, I can probably give you a better example here. Maybe I'm going to take the number 3 as well. Okay, so here you can see that there are two numbers that sum to 11, which is 2 and 9. Right? So the idea is that whatever I see, so I see the number 1, I put it in its corresponding box. 2, I put it in its corresponding box. 3, I put it in its corresponding box. 5 goes here, 7 goes here, and then 9 goes here. And the guarantee is that there has to be a box that contains two items, okay? Because our n is equal to 6. And there's a guarantee, according to our pigeonhole principle, that there is a box. So there's exists a box with this many, so n over k ceiling objects inside. Now, how is this a proof for the statement that we're trying to prove here? Well, the idea is that as soon as we have two objects in a box, the implicit definition is that they sum to 11, right? So that is a proof that in a subset of size 6, there must be a pair of numbers that are in the same box, and therefore there's a pair of numbers that sum to 11 because that sum to 11, because that is our definition of the boxes. Okay, so I hope you can see how useful of a tool pigeonhole principle is. And generally, when we're trying to make a proof that says we must have two objects in a set that has the same characteristic, then we should definitely use something like a pigeonhole principle. All right, so one more example here. So let S be equal to the numbers from 1 up to 200, and let A be a subset of 101. Okay, so I'm going to take a subset of 101. Prove that there exists X and Y so that X divides Y and X doesn't equal Y. Okay, so I'm just saying that X doesn't equal Y here just because we can make a very trivial proof to say that if I pick a subset, the number itself is always going to divide itself, right? So you can't use that one. Okay, but we want to say that there has to be two distinct numbers, x and y, that so that x divides y. All right. So what is the proof here? Well, actually, the proof is quite straightforward, but it is similar to the way that we argued in the last example. Now, remember, every pigeonhole principle question or proof always includes the number n, which is the objects, and k, which is the boxes. So here, let's imagine that we have the objects as equal to 101. So much like the last example where our subset, right, we took out 6 items in our subset, here we're taking 101 items from our subset. Okay, what can we argue about these subsets? Now, this is a hard one, right? This is where we have to come up with the boxes. Now, in my proof, I'm going to generate the boxes as 1, 3, 5, 7, all the way up to 199. And so there are k equal to 100 boxes. Okay, so these are the boxes, sorry. Okay, now what these boxes correspond to is they correspond to the largest odd divisor of each one of these objects. Okay, so the boxes represent the largest odd divisor of each one of these objects. Okay, largest odd divisor. Now I'm going to show you an example in 1 second, but let me just argue here. So the first thing we're going to do is assign each one of these objects into the corresponding box, right? So whatever the number is, the largest odd divisor, I'm going to put it in its corresponding box. Now, note that the number it must have a odd divisor, right? It could be 1, right? In the worst case, it could be 1, but it must have a largest odd divisor. Okay, so the first thing I'll note is that each number, each integer must have a largest odd divisor. Okay, what's next? If an object, if an integer, yeah, we'll say if integer x is placed into box M, right, then we can write x as 2 to the k times m, where k is greater than or equal to 0. Okay, now why is it that I can make this claim? So let's consider prime factorization. Okay, so if I take a number, if I take any integer and I do a prime factorization, that is, I'm going to write the number as a product of prime numbers. Well, what is the only even prime number? The answer is 2, right? There's only 2 as a prime number that is even. So if there are any even prime numbers that in that chain, then it must be a 2, right? So there's going to be a 2, there's going to be a bunch of 2s that are multiplied out, but you can guarantee that the rest of the prime divisors are going to be odd. And what do you get when you multiply odd numbers by odd numbers? You get odd numbers. Okay, so the rest of the number is going to correspond to the largest odd divisor. Okay, so let just maybe rewind that a little bit and make sure you understand what I said there. Okay, so this number corresponds to the largest odd divisor of whatever your prime factorization is. Actually, let's do a quick example. 100 can be written as, so if the number is 100 that we're considering, it can be prime factorized as 2 times 2 times 5 times 5. So that means 100 can be uniquely written as 2 to the 2 times 5 to the 2, which is 25. So 100, for example, would go into box number 25, right, corresponding to the largest odd divisor. Okay, so just take a second to convince yourself that every single number has this. So you might be asking, well, what about a number like 21, right? So a number like 21 has a prime factorization of 3 times 7. Well, it's 21, but our 2 to the k, our k is going to be 0. So it's 2 to the 0 times 21. Okay, so again, I just want you to convince yourself that any number always has a largest odd divisor. Okay, now the rest of the proof should be pretty simple from here. If I consider 2 numbers, okay, there must be 2 numbers in the same box because there are n over k. So there exists a box with this many objects inside. right? So that means there must be two two integers, x and y, that is in the subset of S. Sorry, that is in S. Sorry, in A. That is in the same box. Okay, from the pigeonhole principle, we know that there's at least two integers who are going to be placed in the same box. That is to say that x is equal to 2k times m, and y is equal to 2j times m, the same m. Okay, we're in the same box. So now I hope you're convinced that either x divides y or y divides x. So if k is greater than, or sorry, if k is less than j, then x divides y. But if k is greater than j, then y divides x. Okay, and that is our proof. So again, you could probably look at this proof and say there's other ways to make this proof, and this proof is actually quite obvious if you think about it. But this is how we would use the pigeonhole principle strategy in order to make this proof. Okay. All right. Before we close up for this video, I want to very quickly jump into a white screen and go over something that might be useful for your in-class assignment. So whenever we say that, well, let's take an example from the in-class. One of the questions is saying that how many people are needed, or something along these lines. How many people are needed to ensure that two people are born on the same day? Okay. Now, this would be the same day of the year, has the same birthday. Let's say that. Okay, so instead of born on the same day, two people have the same birthday. Okay, I hope this is more intuitive. Okay, now birthday clearly comes after the word same. So here we can guess that our birthday is the corresponding to the boxes. Now, how many possible birthdays are there? Well, I think there are 366 birthdays. Uh, counting the leap years as well, right? Because theoretically we could be born on February 29th, right? So let's consider that as well. If you wrote 365, that would be right as well. But let's take a look at our n. So our n in this case is not equal to 2. It's actually not known, because what we're told is that n over k ceiling is equal to 2. That's what we're told. Okay. Now, intuitively, kind of implicitly in this question, we are asked to find the smallest n. Now, obviously, if I give you like a million people, obviously there are going to be two people born on the same birthday, right? But what this question is asking is, give me the least n, give me the smallest n, so that this equation is true. Okay, so I'm going to replace k with 366. So what's the answer? What is the smallest n, smallest number n, that this equation is true? Okay, so let's solve it. Well, if you take the number 366, if we take n as 366, that's not enough, because 366 over 366 is equal to 1. And so we take the ceiling of 1, it's still 1. It's not equal to 2. But what if we had one more? What if our n was 367? Now, if it was 367, then it would be enough, because it would be 1 point something, something, something. We take the ceiling, and now it's equal to 2. So the answer would be 367. Now, you might say, well, that's intuitive, right? So obviously, I could have guessed that. But what if I changed the problem a little bit? What if I said, instead of 2 people, I said, how many people are needed to ensure that 5 people have the same birthday? Okay, so again, we're solving the same problem, but this case, we have n over 366 is equal to 5. And again, we want to solve our n is equal to what? Now, the smallest value. So let's use the same strategy that we used it in the previous discussion. What is going to bring me to the boundary? Okay, now let's say we take n as 366 times 4. Okay, whatever that number is, 366 times 4. That number is not big enough. So if we take n and divide it by 366, we get the number 4. Right? So ceiling of 4 is still 4. But what if I add just one more person to this? Well, now it's just above 4. So if we take the ceiling, it's now equal to 5. So this is the smallest number that will round up to 5. Okay, so generally, the equation that we take would be the k and whatever this number is. So this number, let's call it x. Okay, so k times x minus 1 plus 1. Okay, so if you're ever wondering how many objects will I need so that there are this many objects in the same box, right? If you get this type of question, then this would be the equation you would use. Okay, so I hope that's helpful for the in class. All right, so let's stop the video for now, and I will see you in the next video.